Okay, so let's start. We have the Zoom session. And let's introduce the first speaker, Nathan Geer from Utah University, who's going to talk about renormalized TQFTs.
Thank you. Thank you for the organizers. It's a pleasure to be here. And so, first I just wanted to start off with a general idea. So, the first thing we let Q be a complex number. And the usual, you have the Resch and triad invariant. So, string invariant. This is a map. You can think about it as a map from certain colored links to the complex numbers, and if you want more precisely, this Q can become this kind of a variable, and you take the power series Q and Q inverse. And this could be thought of as a generalization of the, depending on what colors you have here. So these colors are labeled of the strands or the components with modules from or over quantum SL2 if you want. This generalizes, of course, to other algebras, but this is the setting, and this can be thought of as these are generalizations. So these are kind of Jones polynomials, and when the main part of the talk, what I want to talk about today is when Q is a root of unity. So different things happen. So when Q is not a root of unity, you get the usual Jones polynomial. And then when Q is a root of unity, you actually have three manifold invariants. And this is the setting I want to talk about. So when Q is a root of unity, we have modular categories. And these modular categories, they give rise to three manifold invariants, so that F leads to three manifold invariants. And TQFTs, as Geer talked about in the last talk. And you can think about these modular categories as really being some category modded out by projective modules. And so in this talk, you have projective modules and simple modules, and some kind of category generated by these. And I can think about this as a sort of exact sequence here. And these modular categories are exactly these, all the things generated by projective modules and simple modules, and you mod out by the projective modules, and you get these modular categories. And so what I actually want to talk about on this talk is what I get from these projective modules in this case. And so here what you have is F can be renormalized to F prime, which leads to three manifold invariants and TQFTs. And this is what I want to talk about today. What this story is. So, the first thing that you might say is, well, Well, why do we want to work with projected modules? This is still all the introduction. So why renormalize? And the main idea is that, well, it gives different information. So these variants. Different information than usual invariance, Russian TQFT type invariance. So in particular, the first thing is that these invariants, these link invariants, look more like Alexander polynomials than they do Jones. So this looks like Alexander polynomials. The second thing is that these three-manifold invariants, the ones that have the renormalized three-manifold invariants, distinguish distinguish lens spaces. For example, in 3, these TQFTs give you information on mapping class group representations. So for example, in the last talk, new mapping class. Group representations with properties, with different kinds of properties. So for example, as I'll explain, in the last talk, Gregor talked about what that first question he wrote on the board was the mapping class groups linear. And so I read some paper recently by Joan Bergman, and she said, can you even find a candidate for a linear representation? And this is a candidate for a linear representation. At least we can show that if you take a separating curve and look at the Dane twist on that, it has infinite order, which is very different than the usual Rush-Deacon drive, which all have finite order. So there's some hope. We can't see, we have no idea. I feel it's probably very difficult to prove that this thing is actually linear. But, you know, at least we can't see anything in the kernel. So it's possible that this is that does give a faithful representation of mapping class group, finite dimensional. So these are some reasons to maybe want to think about these things. Also, there are some more physical information, more physical reasons that Christoph knows about, but he's more comfortable with these things. So I think there are some relationships there, but I don't speak about those type of things. Okay, so now I go on to, so that was the outline here. And now I'll do part 2 of renormalize, so the linking variant. Okay, so the first thing we need here to talk about the linking variant is we need some algebra. And so we use a slightly different algebra than I said over here. You know, we want to build, we can start with something like this F. And this is the main idea. So we let Q be a root of unity, I guess is the first thing. So we have Q. I'll fix the root of unity to be e to the pi over r, where r is some integer. So this is a 2rth root of unity. And now what we want to do is I want to say what these colors are. And so here before we used quantum SL2, and I'm going to modify quantum SL2 just a little bit to have a little more information, to get some more modules, to help us with this renormalized business. So the algebra I wanted to find, so define UQH of SL2 is the following algebra. So it has generators. E, F, H, K, and K inverse. So it's a mix of SL2 and quantum SL2 in the following way, so it has some relations. And what are the relations? Well, first you have H, E, this is 2E, you have H, F, minus 2F, you have H and K commute, plus or minus. And so this looks a lot like the SL2 structure. So the big H is really, these things look like SL2, except that, well, you don't have, if you look at E and F, it's a little different, as we'll see. So what's E and F? E and F now looks more like the quantum SL2 part. So I have this relation, which is the normal relation in quantum SL2. And now I have K, I have K commutes with itself, K inverse commute. And they're equal to 1. And now I have the usual relations with H, with E and K also. So what's E and K? We have K inverse is equal to Q to E. So this is the quantum part. So in K looks like this. And actually if you look at this for a second, it looks like what we're modeling here is that K looks like Q to the H. And that'll make even sense in a little bit more. We're taking some kind of exponential. K is the exponential of H. So now we think about it. And that'll make sense when I define the module. So this is not precise, but it's the idea. And so then we also we want to deform this also to K. So when I deform that to K, I get K. K inverse is equal to -2 Q to the -2 F, and I believe that's all the relations. Yeah, so those are the relations for one.
So in this way, K and H are not really connected to each other, right?
Not yet, but you can see from the relations that you want them to be. And now we define them to be the same on the modules. So now I want a relationship with the modules.
So you don't want to add this relation K is equal to Q to the H because it's transcendental?
Yeah, it doesn't make sense to say Q to the H. What is that really?
Yeah.
So instead we do it like this. So I say here, so now we define the modules, and here I will define that relation to be true on modules. So what does that mean? So modules. So we let C be the category of U, Q, H. So I want to say U, Q, with which are finite dimensional and have H weight decompositions or spaces. And such that E to the R, F to the R, 0. And finally, the final condition is that K acts as Q to the H. And what do we mean by that? We mean that, well, since I have a weight space decomposition, it means that, that each module is a direct sum of its eigenspace, of H eigenspaces. So I can take, if I want to define, it's enough to define this on just the H eigenspaces. So I have K of P, this is going to look like Q to the lambda V, where H V equals this complex number, that eigenspace. So if I look at that eigenspace, then on that eigenspace, K acts in the way you want it to act. So that's the category of modules. And now, so a few things about this, some properties. So first, simple modules. Are in one-to-one correspondence with complex numbers. So there's one for each highest weight. When I make these act by 0, then I get highest weight modules. And there's exactly one for each complex number, depending on how, for each value here, there's exactly one highest weight module of that, and it's simple. Well, I said I was going to talk about projective modules. So indecomposable projective modules there's also one of these for each of those simples, and so these are also they're also in one-to-one correspondence with C.
And
There's one for each simple object. Yes?
And for which complex numbers are they finite dimensional?
All.
All.
All finite dimensional, but yeah, so I'm only considering finite dimensional
Oh, yeah, so.
cases here. So yeah, this is that's a good question though, because if you look at the usual theory, then some of these modules, you have Berman modules that would not be finite dimensional. But when you require, so when we go to this special space, then we get, well, when you go to the root of unity now you get, when you go to the root of unity you get finite dimensional. Eventually it's a force, even if you don't have this requirement, sorry. Even if you don't have this requirement, you still get finite dimensional, but there are a whole bunch of extra ones if you don't require that. Get these cyclic modules, different things like this. So anyway, we don't talk about those. But so third thing I wanted to say about that. I guess that. No, so I guess I want to say about the modules. So now I can tell you how to compute the invariant and where it comes from. So. How to compute in the link. Yes?
Can you say for which values of C the simples are projected?
Yes. So, if okay, so there's one more point, but if this happens, then the alpha is simple and projective. And if you want more details, I can tell you more. There's one more point also, but that's an important one. So how to compute the link invariance? So I'm not going to exactly define it, but I'll at least tell you how to. Okay, so the first thing is we have F is this Reshatiya Dryad invariant. Associated to this category C. So there exists already a Reshatiya Dryad invariant. Then you might say, well, why didn't we just use this one to begin with? And it's the following property is that, oh, so how is this thing constructed? So this thing has a few of the other talks I talked about. You take a diagram and you represent the diagram with this crossing. This category turns out to be a ribbon category. So there's some Young-Boxster operator here, as Joseph talked about. And then you also have some maps like this. And so you write this as a big tensor product in one direction and then composition in the other way of your link. You compose all these things and you get a morphism in the category, and then this morphism is the link invariant. Well, and if it's closed, then you get from C to C a morphism from C to C, which is a complex number. Okay, so the first thing to notice is that if you take F of a projective on the unknot, for any projective, this turns out to be 0. So this makes basically everything on the projective, that whole category, everything with the color with the projective 0. Let me explain why that's 0. So you have F of L, and say L has color with some projective, and I have F of. So it looks like I have some mess here, and I have some projective. Now, for the properties of this functor, this from here to here, it's a morphism from P to P. So that's a morphism from P to P, which is just a scalar, then if P is simple. So P is simple by Schur's lemma, this is just a scalar. And then I just have the unknot otherwise. So I have that scalar times the unknot. So this looks like F of 0 P times the scalar thing inside here is endomorphism of P, which is just isomorphic to complex numbers, so that's just a scalar. So since if this thing is 0, then anything colored with a projective, even if it has other things on there, is always 0. Yes?
What's the dimension of those projectives? Is it R?
So yes, here for all these ones is R. So these all have dimension. And so, well, so it looks like I made a small requirement to say simple, but actually you can say all these things about simple if you want to be a little fancier. And this formula, to see that this is 0, it just comes from these formulas. It's very easy to just see that you just get you're adding up a whole bunch of roots of unity, and the roots of unity just cancel. That's what happens, essentially, something to this effect. So, it's a little more complicated, but basically just. Okay, so, what's the idea? What we want to do here is, I want to, since this thing is 0, what I want to do is replace this. With something non-zero. And so this is what I.
And what if I took not simple but projective?
See 0. This is always 0, and you can do a similar argument, so you just get some kind of, it's a little harder to show, but it turns out it's 0 for any projective. If you have a component color of the projective, you get 0. It's a little more harder to show, but it's not quite as clear just to see the scalar, but you still get 0. So it's 0 on the whole subcategory of projective modules. Okay. So, the idea is to try to replace that, and this is what I did with Drive and Petrov. So have the following theorem. There exists a D function from the set of projectives. Well, we might as well just, you can do it from everything, but let's just say simple. To C, such that f prime of a length, I write that, so I need to have one color with the projective on it. I need a simple projective on one of the components. So it looks like I have something here. And I have a projective on the outside somewhere. I can write it like this. And now I can cut here. And when I cut here, I put D of P. And then I take the scalar. Corresponding to f of this part, and this is a well-defined invariant. So it does not, so this is with so this is a well-defined link invariant. So it doesn't matter which component I cut or where I cut on the component. I cut any projective module and I get a well-defined invariant. And it's not zero. And it recovers the Alexander polynomial, also has Kashaev's module. I mean, Kashaev's invariant inside of it. It's a different kind of invariant than before. So, now we want to use this invariant. So now the idea is we want to use this invariant to make a three-manifold invariant.
So you meant the second f to be prime too, or not?
Sorry, what?
There's no prime on the second f? Because you
Oh
just
yeah,
said
no, I
this-
showed the prime there, sorry. Thank you. Now this one, no.
Yeah.
This one, no, but yes, you're right. That was the definition, sorry. Thank you. So f prime is the renormalized invariant. And you can see it's called renormalized because we just replaced this thing that was zero with some other function that has enough of the good properties that you can cut wherever you want. So it looks just like a quantum dimension, except it has a few different, well, it's non-zero first, is the most important part, but it also has all the good properties of the quantum, or a lot of the good properties of the quantum dimension. I guess one thing you should notice here, another property about this thing, is that, well, I guess f prime of, if you have split links, is still zero. Because even if I've split links and I open one of these components, this still has a projective on it. And it's disconnected. So it's still zero. So you still have multiplicative property still applies this is zero. So this is why it also looks like the Alexander polynomial. Alexander polynomial was one. It's not why it looks like Alexander, but I mean, Alexander does have this polynomial property. Okay, so we want to try to make, you can see right away from that it's hard to make a three-manifold invariant. Because if you want the three-manifold invariant to have the Kirby moves, well, the Kirby moves have split links, at least in the normal formulation, but you can fix this, but I'll explain how that goes. That's not the hardest part, but you can see that's an issue. Okay, so now I go on to part, or is there questions at this point? So I go on to part 3.
Sorry.
Yes.
For the function, d of p, can you say?
Yeah, you can give an exact formula. It just depends on alpha and q. You can give a complete formula. It depends just on the character. It's the specialization of the character of the module.
But do you want to write it, or is it?
I don't want to write it down, but it's not so bad.
Okay, well.
I don't know why I have it. I'll show you later. It's not so bad. It's easy to write down. It looks something like a quantum dimension with alphas involved. It looks very similar to this. So, okay. Embarrassing. Okay, so what Reshetikhin and Triumph did is they said originally they took Jones polynomial, or cablings of the Jones polynomial, colored Jones polynomial, and took sums of this with quantum dimensions as weights, and then they showed this was a Kirby. This satisfied the Kirby moods, this sum of invariants. We want to do the same thing. But what do they do actually? Because I said they mod it out by the projective initially. When you mod, to get a modular category, when you mod out by the projective, you only have a finite number of simple modules. So this is one of the first problems you have to deal with, is you need to deal with this problem of finite number of simple modules, but I'll explain this as we go. So the first thing you need is a Kirby color. So we have these modules here. We have these simple modules are here. So I have B alpha, and I correspond that to an alpha in C. Now I'll go back and forth between these two notations because sometimes it's easier to write alpha, sometimes better to write B alpha. So I'll just go back and forth with these. So I can color, instead of coloring with the projective, a link with projectives, I can color it just with an alpha, where alpha is a complex number. Keeps track of the same information. Okay, so for alpha in C mod minus Z, so this goes really back to his question, when are these things, when are the projectives simple? So we need projective modules, but we want to stay within alpha 1, I want it to be projective and simple. So it really comes down to this. So for alpha and C, we want to define the Kirby color in the following way. So I have this Kirby color, which is the sum over some indexing set, which I'll do in a second, of D of alpha plus K. So this is really just D alpha plus K. That thing is defined for projective modules. And I take alpha plus K, where this is in the span, C-span of formal combinations of so I just take these formal combination here, formal linear combinations, kept track of by complex numbers, and I weight them with this B. And what's H? HR is equal to 1 minus R, 3 minus R, and R minus 3, R minus 1. So it's just this set. This is just keeping track of, this looks a lot like the usual color, the usual Kirby color, except you don't have this alpha involved. The usual Kirby color would just have K's here, and this would be the Kirby color. So we put this alpha in there, and then we get this. So now we want to color that with a knot. So how do I do that? So given a knot K, define K of this Kirby color to be, again, the formal linear combination where I take the sum K over H of D alpha plus K, and now I color the knot K with alpha plus K. So this is the knot K colored with alpha plus K. Okay, so now I can extend to such a knot, I can extend the invariant f prime to such a knot. Let me explain how to do that. Pretty easy. So, f prime of k of a Kirby color is just equal to, I just take this coefficient out front, I should still continue to take the sum. And now I have f prime of k alpha plus k. So I extend f prime this way. And similarly, you can do it for length. Now I need some. So the idea now, you want to take a three manifold. Well, I need to get a finite number of modules. This is a finite number of modules. But I've chosen some alpha here somehow. So somehow I need to have this depend on the manifold or have some extra data that keeps track of that. Yes?
So the understanding correctly from that formula, you have actually d squared, right? Because there in
Yes.
f prime there is a d, and
Yeah.
here there is an extra d.
Yeah, you get a lot of these. And you'll see that in the first example I do when I compute it, you'll get a d squared. You'll see that exactly. Okay. Okay, so now, yes, okay, so the data of the three manifold invariant. I need more than just the three manifold. So I need M. I want a link inside M, and I want a cohomology class. Let me write this down. So and so this is connected. Lots of nice properties on this. You have lots of nice properties on the three manifold. So I have compact, connected, oriented three manifold. I also want then T to be inside M, a link, a C-colored link, and I want this to be a cohomology class of M minus T with coefficients in C star. So this is the data that I need for the three manifold invariant. And now let me tell you how I define it. So the normal thing what you do when you do the Resch-Tiken drive invariant is you take your manifold, you take a link presentation that represents that manifold, and you decide you sum over all possibilities of that Kirby colors. You put Kirby color in each component and you sum, and that's some kind of sum, and then this is the invariant. So we want to do something similar, except I need to fix the finite number of modules using this and the cohomology class. So let's say that let L be a surgery presentation of M, I guess I'll say this is the union over Li, so it has, these are the different components of that surgery presentation, such that W of Mi is not an integer, where Mi is a meridian of Li. So I take a meridian of Li, of a component, and then this cohomology class gives me a complex number, and I want that complex number to not be an integer. Okay, we're making a big assumption there that even such a thing exists. But if you're given such a thing, now I can color each of these components with the Kirby color. So, color. Color Li with that Kirby color coming from that meridian. Okay. Now, what the theorem is, so this was with Constantino, myself, and Patrick Rowe. And what we say is that n of m t, this cohomology class, which equals f prime of L union t. So this thing makes sense now because L is colored with the Kirby color. So it has at least one projective, and I have t. And now I need to divide by some constant that only depends on the linking number of L. So this is just a constant that depends on the linking number. This thing is a well-defined invariant of m, t, and omega, meaning it only depends on the homeomorphism class of this. So, this is the theorem. Yes?
Can you take
Yes, but then you need a restriction on the cohomology class. You need some kind of genericity. You need something on the cohomology class. So I'm not going to say what that is exactly, but you can take t to the empty. But you need a little, we need still projective to show up. So you have to force projective to show up in some way. And you can use cohomology class to do that. If t has a projective on it, then every cohomology class works.
So there's no correlation between the coloring of T and omega.
No, there is. I didn't say that, but since you asked, you need, so when I restrict the cohomology class to T, it needs to be the same color. So I need that to happen, yes. So there's, and a little bit I'm hiding something in C star also. There's kind of some different gradings going on, and I'm hiding a little bit of a grading issue also. But it just gets complicated, it won't help you. But if you want to know later, I can tell you precisely what that is. Yes?
So maybe you are going to talk about it later, but what kind of function is this on the first cohomology? Is this like some sort of linear function? Or?
Yeah, it's continuous. Well, I mean, it's as you vary the cohomology class continuously, you see it as a variable in Q to some powers that are continuous.
I see, but it's nothing simple. Nothing. There's no simpler, stricter class of functions.
No. So let me give you an idea of how the proof of this goes. So I just erased the fact that if you have split links, you get 0. Oh, I guess first of all, maybe I should do a couple examples first. So the first example is M S2 cross S1 TMD, and we have a generic cohomology class. So what I mean here by generic, well, here L is unknown. of this three manifold, when you take the Serger presentation, you get L as an unknot. And so I want this cohomology class, there is some, I want the cohomology class to be non-trivial on this, non-integral on this length. So, suppose that W of M is not in C mod Z, or C minus, it's in C minus Z, where M is a meridian of L. Okay, then, N for this example is equal to, well, what do I do? So I just have F prime of the unknot colored with this. I just have the unknot and I color it with that Kirby color. That's what the definition says to do. So we took L, we colored each component using the cohomology class. So in this case, I just color Li with L in this case is just unknot. I color it with this Kirby color, and now I compute. So what's this Kirby color? This Kirby color is just that sum, and so this thing is just equal to the sum of K HR D omega M plus K times F prime of the unknot colored with alpha plus R. And now this is just D again. So I just have this thing squared. And that's that invariant, simplistic variant. So. Again, we'll take S2 cross S1. This time we can take T to be the, they call the Whitehead double. Of the core. And this will be colored by some beta. And then we also take a cohomology class. So let's say this beta is just, well, okay. That doesn't matter, I guess, in this case. So let's just assume we have, again, some generic. In a similar way as we have above, we have a generic cohomology class. Just making things simpler, otherwise, as the proof we'll see. So this is. Okay. So now what do I get? So now I want to write this thing. So N, in this case, is equal to F prime. So again, here L is just the unknot, but now, so I have my S2 cross S1, and I have inside the S2 cross S1, I have this link that is this, and so now the unknot is going to go around that link. So what does it look like? It looks like I have this. And here I have, this is omega of m, and this is beta. And so now again, I just expand this using omega and then compute. And in theory, you can actually compute this. We give some formula for this also, but I will write that down. So this is the idea behind the invariant. So let me maybe give an explanation of, well, I probably only have time to either talk a little more about the TQFT or give an explanation of the proof. So I haven't even gotten to the TQFT, so maybe I should do that instead of give an explanation of the proof. So,
Normally you at the end.
oh, I thought, I only have 50 minutes? Okay, then I stop there.
Okay, so thank you very much. Other questions?
So I'm still wanting to write about the explanation, just what was the kind of big things that you, or whatever, main trend you wanted to present? Like, well, why does it work?
Well, the main reason why it works is so you have this main condition. So that's a good point. So, I mean, I have this condition here that I need the surgery presentation to always have values outside of integers. And so the main idea, what you do is you take your link presentation to get such a thing. You take your link presentation, since you have a projective somewhere, you can put a new component with make a new hop link. And you can choose this generically, it turns out, the color you put on the hop link. And now you can slide, the sliding properties work, and you can slide that over all the other components. And when you slide that over the other components, then it changes them by that complex number. And then you can make a generic presentation. And essentially, this is how you also prove, when you're doing the property of proving that the invariant exists, you know if you have two different link presentations, they're connected by Kirby moves. But when you start to do those Kirby moves, you might go through a bad place. But you can just do the same idea. You can do a hop link, pass it over everything, and know that you can do that in a generic way. Do the Kirby moves, then unslide, and then you get back to the same place. So this is that's the main takeaway.
So this will be defined for any non-zero omega or no?
For if it does not, as long as it does as a non-integer value, it's always defined. Otherwise, if t has a non-integral value, if t has a projected module, then it's always defined. And there's some intermediate values in between, but otherwise it's difficult. So it's not defined for all omega and all t. There are restrictions on omega and t, but they're relative well. Okay. I'm working on trying to get rid of this restriction, but it's difficult when the cohomology class is 0 and t is 0. This could be a challenge, but I'm working on trying to do that. It's possible, but I'm not sure.
So maybe I can ask a question myself. What is the relation between the theory you are presenting and equivariant TFTs or homotopy TFTs? Because in many respects, your construction looks as if your theory is equivariant over the group C mod to RZ.
So,
And you're adding a line bundle as an
yes,
additional data.
that's exactly what we're doing. So what was your question?
So should I think about this as a version of a homotopy theory?
So it does look like a homotopy theory, except it's abelian, right? So if you look at like what Alexi will be talking about next, then you can have the braiding might not be abelian, right? V tensor W is not W tensor V, and so we have that property. So it actually looks like some kind of, I believe it's Chern-Simons theory. Maybe the way that makes sense to you is Chern-Simons theory of SL2C, except only the abelian part diagonal. Something like this. But I don't really know how to make that precise, but this is like Bezier and Benedetti will be things like this. Did that answer your question? Yeah.
Okay, so if I don't see any more questions, then let's thank the speaker again.